In this video, we'll discuss the synthesis of ethers. So there's several ways that we can make ethers. One way is by using two alcohols in an acid-catalyzed solution to give us an ether and then an equivalent of water. As an example, we could use butanol and put this in solution with an acid catalyst, probably H2SO4. Sometimes you heat this a little bit. What you end up getting is an ether plus an equivalent of water. So the first thing that will happen is that water will get protonated. It's a poor leaving group. So if we make water, we can make a good leaving group. And so this is going to serve as our leaving group, and then another equivalent of our butanol is going to come in and act as a nucleophile. So this guy comes in and attacks that carbon and kicks the leaving group off. Now that's an SN2 style reaction, which happens because we have a primary system, so it's unhindered. This can also proceed through an SN1 reaction if we have a more substituted alcohol. So now we've got our ether, but it's just protonated, and we spit out an equivalent of water. We're in acidic solution, so water is the best base that we have, so that water can deprotonate and get us up to our ether. So if we have a primary, we're definitely going to see an SN2 mechanism for this type of reaction. Secondary can be SN1 or SN2. It just depends on how bulky the substrate is. And a tertiary system would definitely be SN1. It's too crowded for concerted attack while the leaving group leaves, and a tertiary carbocation is relatively stable. We can also synthesize an ether from an alkene and an alcohol under acidic conditions. So in this case, it would be the alkene that gets protonated. So depending on what alkene you use, if you use an asymmetrical alkene, you can be sure of what carbon is going to end up with the positive charge on it, because it will give you the most stable carbocation intermediate. In this case, let's take this guy and we'll add methanol under acidic conditions. So we already know that pi bonds are reactive towards acidic conditions. So that pi bond can become protonated. The H will add to the terminal carbon and give the more substituted tertiary carbocation intermediate. So this is our electrophile. And then methanol is going to serve as our nucleophile. So that methanol will come in and attack that electrophilic carbon. I'm going to drop off that H that I had already drawn. So there's my CH3 and my H+. So under these conditions, I pretty much have my ether again. I just have to deprotonate, and so I do have a bunch of methanol in solution. There's probably also a little bit of water, given that I'm in acidic conditions with H2SO4, which is often has some component of aqueous to it. So I'll go to the next slide here, but here's my deprotonation step. And that gives me my final ether. So depending on what alkene and what alcohol I start with, I can synthesize a variety of ethers. So my alkene in this case generates the electrophile by becoming protonated by the acidic conditions, and my alcohol is the nucleophile. And of course, if the alkene is asymmetrical, you'll see the most substituted carbocation form, because it is more stable, so we can avoid getting a mixture of products in that way. Another method for synthesizing ethers is called the Williamson ether synthesis. And this is done under basic conditions, and so here I have an alkoxide ion. So alk for my alkyl group, and oxide because I have that negatively charged species, and then I need to have something with a good leaving group on it. Usually we use an alkyl halide here. So in this reaction, just an SN2 reaction, the alkoxide ion is our nucleophile, X is our leaving group, and we get our ether over here, and then our leaving group. So as a specific example, we could take this system. We've got our alkoxide ion comes in, our leaving group leaves. I'm going to go down here. And that gives us our ether. Now this will only work for methyl and primary RX. That doesn't look like an and sign. Okay, so to think about why that is, we need to think about OR minus. What kind of a base is OR minus? It's a strong base. So if I have a strong base and a secondary or a tertiary RX, you got to remember back to OChem 1 to think about this, but remember that a base has to come to the periphery of the molecule to grab a proton, whereas a nucleophile has to go all the way in. As the substrate gets more hindered, we're more likely to see elimination products with strong bases. So because we have an alkoxide ion in this reaction acting as a nucleophile, it will only work with unhindered systems, methyl and primary RX. If we have a strong base with a secondary or a tertiary RX, then we end up getting an E2 elimination reaction, and we generate alkenes instead of substitution reactions that yield ethers. Lastly, I want to talk about the acid-catalyzed cleavage of ethers. So ethers are not particularly reactive. They're often used as solvents for that reason, but you can, under acidic conditions, sometimes get them to react. So this is acidic catalyzed cleavage. So what happens, and I'm going to use an asymmetrical one so we can figure out what's going on here. So we have 1, 2, and then we have 1 prime, 2 prime, 3 prime. If we put this in solution with 2 equivalents of HBr, I end up generating 2 alkyl halides. So I would have ethyl bromide plus propyl bromide plus H2O. So 1 and 2, the way that I had labeled it, and then let's see here, we have 1 prime, 2 prime, 3 prime. So I've cleaved that, and then water served as my leaving group. I was under acidic conditions with the HBr, so Br will eventually act as the nucleophile. The H will protonate the oxygen repeatedly so that it's a good leaving group. So if we look at this mechanism, my first step is to protonate. To give me a good leaving group. Now it's going to be an alcohol that's my leaving group. In this case, I have on either side a primary carbon. So there's not really going to be a difference in which one leaves first because there's no selectivity there. The more substituted the carbon, the more quickly it will leave because it will leave behind a more stable carbocation. In this case, it doesn't matter. We're going to get the same products anyway. So I can show this leaving group leaving. So that will give me ethanol. And as that leaves, bromine is going to come in so that I can avoid a primary carbocation. So that gives me my propyl bromide. Then we've got this second equivalent of HBr in there. It's going to protonate the oxygen. So now I have a good leaving group, and this is where my water comes from. And then again, this Br minus can come in and attack. And we get ethyl bromide plus water. So this is dependent on the substitution. Primary, again, will go SN2. Tertiary will definitely go SN1. And secondary can go either. It depends on how bulky the substrate is. So we can't really guess as to what it is. But water is a pretty good leaving group with that positive charge. So you often see SN1 reactions with the secondary system.